So I'm going to start off, and in this video I will do maybe 3 different relative dating techniques, and then I'll do the rest of the relative dating techniques in the upcoming video. I'll start off with the first technique, which is the law of the law of superposition. And so if you were to look at this stack of books on the left side of the page, and if I said to you, which book was placed first? Hopefully you would answer the book on the bottom. And if I said to you, which book was placed last? You would say the book on the top. Now, if you were to substitute these books for different sedimentary layers, then naturally the sedimentary layer on the bottom would be the oldest. And as you move up through the different books in this particular direction, the books would get younger in terms of how they were actually stacked. The law of original horizontality states that every single sedimentary layer forms flat. And so naturally, horizontal means flat. So originally, sedimentary layers, when they are deposited, now most times sediment gets deposited in layers in water. So it could be at the bottom of an ocean, at the bottom of a lake, at the bottom of a pond. Also, those sedimentary layers could get deposited not in water, for example, in a desert, in a sandy desert or something like that. If you were to look at the particular diagram here on the left, I know that layer A, layer B, and layer C were actually formed this way. And so looking at that diagram, you can tell that they have not been disturbed. The law of superposition would say that this right here is the first layer that got formed because it's on the bottom. This would have been second because it's above it. And this would have been the last layer that formed since it's on top. And so this would be the oldest layer, and as you move up, the layers get younger. Now, what I'm applying there is the law of superposition. I'm not applying the law of original horizontality. I don't really need to, because in this particular diagram, all the layers are flat. So they're the exact same way that they were originally when they actually got deposited. If I look over on the right side and I look at this diagram, I see that the layers are not flat. In fact, they're folded. And for people who've probably studied folds before, you'll notice that this is an anticline. I always remember an anticline because if the layers are folded up, you could actually put a stroke across like that and create an A. A stands for anticline. So when you look at a certain layer, like this particular layer right here, that layer is not flat, it's folded. So we know right away that based on the law of original horizontality, it got moved or folded after it was deposited, because we know originally it would have gotten deposited. This particular diagram just indicates that sediment first has to get created, and it gets created by a process called weathering. There's 2 different kinds of weathering, physical weathering and chemical weathering, but you don't really have to know that in this course. So weathering is the process of grinding rocks up into little tiny pieces called sediment. The sediment has to get moved. It gets moved or transported by a process called erosion. So in this particular diagram, when I look here, I see some glaciers that could do the erosion. I see some rivers and streams that could do the erosion. And eventually, it all gets transported out into a water body. So if you remember earlier in the video, I said that most sediment actually gets deposited in water. And so as you can see here, that this sediment is getting deposited at the bottom of Playa Lake, right here. If you were to look in on the diagram in this little area right here, you'll see the formation of different layers. And those layers are all forming flat or horizontal to prove the law of original horizontality. This is a picture of a cliffside, and actually 2 things are taking place here. I can tell that all of the sedimentary layers are flat, which would indicate to me that they formed this way and they haven't really been disturbed at all since the time they first got deposited. Also, I could apply the law of superposition, which would state that the oldest sedimentary layer is on the bottom, and as you move towards the top, in this case towards the sky, the sedimentary layers get younger. So in this particular case, I'm applying the law of superposition. The law of superposition was actually proposed by Nicholas Steno, and Nicholas Steno stated that a sequence of sedimentary layers that have not been disturbed. So if you can prove that the sedimentary layers have not been disturbed at all, then you can go ahead and apply his law of superposition, which says that the oldest layer is on the bottom and the layers get progressively younger as you go up. So over in the diagram on the right, we actually have absolute dating and relative dating. Over here, this is absolute dating, which is not really a topic for this video, but remember, absolute dating actually gives you numbers. Law of superposition is an example of relative dating. And so if I looked at this sequence of different sedimentary layers, you can see that the oldest one would be down here on the bottom, actually just off the screen. And as these layers go up, 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 they get younger and younger. This is more what it looks like in real life. You got to remember that geology is not perfect, and if everything was perfect in nature, then the science of geology would be easy. So you can see these people down here. So we have a person here, and we have two people right here, and they're staring up at this rock outcrop, and hopefully you can see from this rock outcrop that it is sedimentary layers. It would be really difficult to apply the law of superposition here. What you don't know is this the oldest layer, and as you go this way, they get younger, or is this the oldest layer, and as you go this way, they get younger? You don't know, and as a result, I would be very skeptical to actually apply the law of superposition. There is a way you can get in here as a geologist, and there's different clues that you could look for that we really don't cover in this course, but different things that you can do and look for to tell you which is the top and which is the bottom. So in this particular example, over here is the top, and over here is the bottom. And if that is the case, if this is the bottom, then we know that this is the one that's actually true. The oldest would be here, and as you go towards the top, the layer. There's another principle called the principle of cross-cutting relations. There's two things in this course that can do cross-cutting. One is a fault, and one is an igneous intrusion. And an igneous intrusion that is vertical, we call an igneous dike. So if you were to look at the diagram down in the bottom left corner, we can see a fault. So here's the fault. I'll try to trace it as best I can. The fault kind of goes along this line, and a fault is something that cuts layers. And so if you were to look at layer A, B, and C, for example, they don't line up perfectly because the fault actually moves the layer up and down. The other thing that you'll notice is that there's an intrusion right here and right here. And the intrusion cuts through the different layers. The easiest thing to remember is that nothing can cut something that is not there. So if you had a knife, how can you cut a cake if there is no cake? So how can a fault cut layers if the layers are not there? How can an intrusion cut through layers if the layers are not there? If I had to interpret the geology on this side, what I would say is layer A came first, then layer B, then layer C. Then I would say that the intrusion came through. I know the intrusion came next because I can see the intrusion cutting through A and B, and I can also see it cutting through C. It doesn't go through D. That tells me that the intrusion is older than D. Next, I would go with layer D, and after layer D, then I would go with the fault. I would put the fault after D because the fault stops right here at the top. It doesn't cut through E, so I know that the fault is older than E. So to repeat that, I would go A, B, C, intrusion, D, and then the fault comes up and cuts everything. So it cuts A, it cuts B, it cuts C, it cuts D, and it also cuts the igneous dike. Then you would have layer E placed on top. So that is just an example of me using the principle of cross-cutting relations to interpret the geology of that cross-section. If you were to look here, this is a picture of rock layers that actually exist in real life, and you can easily see there's a fault here. So to match this up, this little layer right here matches with this one, and this one with this one, and this one with this one, and this one with this one, and so on. So naturally, if these two here match up, then that one went that way, and the fault fell down that way. Okay? So the biggest thing with the principle of cross-cutting relations in this video is that the fault had to come after all of these layers, because all of these layers are actually moved, they're broken. and displaced, and that could only be if the fault came later, were there first. Similarly here, you can see that this particular layer right here matches up with this layer. So obviously everything on this side got shifted up and everything on this side got shifted down. So this layer, it formed based on the law of original horizontality as being flat, but naturally movement occurred later, so the fault came after these layers.